There is a smallest possible distance in the universe, not just something incredibly tiny, but a distance below which the idea of space itself stops working. Below this scale, you can't talk about here or there anymore. Distance loses meaning, time loses meaning, and the laws of physics stop agreeing with each other. This distance is called the Planck length. It is not important because it is small. It is important because it marks the edge of reality. Tonight we are going to walk step by step toward that edge, not with equations, not with heavy mathematics, but by understanding why science is forced to stop there, and why going smaller doesn't just become difficult, it becomes meaningless. For most of human history, reality felt solid, smooth, and endless. If you took an object in your hand and broke it in half, you still had something real. Break it again, and again, and again. No matter how small the pieces became, they still existed. Nothing in daily life suggested that this process would ever truly stop. This created a powerful assumption that reality is infinitely divisible, that between any 2 points, there is always something smaller. That space itself is smooth, continuous, and without limits. This assumption felt so natural that it went unchallenged for thousands of years. The reason was simple. The limits of reality were the limits of human senses. Our eyes could only see so much detail. Our hands could only feel so much texture. Below that scale, the world simply disappeared from awareness. But disappearance is not the same as non-existence. The first major crack in this assumption came with the invention of the microscope. Suddenly, objects that looked smooth were not smooth at all. Living tissue was not continuous. It was made of tiny structures called cells. Each cell was alive, organized, and complex, yet completely invisible to the naked eye. Reality did not end where our senses ended. It continued quietly beneath. As microscopes improved, the story repeated itself again and again. Cells were not fundamental. They were built from molecules. Molecules were made of atoms. Atoms, once believed to be the smallest possible units of matter, turned out to be mostly empty space. That discovery alone was shocking. Matter was not solid. It was structure suspended in emptiness. Inside atoms was a dense nucleus surrounded by electrons that did not orbit like tiny planets, but existed as clouds of probability. Objects stopped behaving like solid things and started behaving like patterns, chances, and interactions. Then even the nucleus was not the end. Protons and neutrons were discovered. Then quarks inside them. Reality kept opening inward, layer by layer, each one stranger and less intuitive than the last. At every step, scientists asked the same question. Can we go smaller? For a long time, the answer kept being yes. But something important changed as science pushed deeper. At large scales, breaking things apart is gentle. You can cut a stone without altering the laws of physics. But at small scales, breaking things apart requires energy, and that energy begins to matter. To see smaller details, you must use shorter wavelengths. Shorter wavelengths require higher energy. Higher energy disturbs what you are trying to observe. At the smallest scales, observation is no longer passive. It becomes violent. The act of looking changes the thing being looked at. Measuring position disturbs motion. Measuring energy disturbs time. Reality refuses to be inspected gently when you get too close. This is where intuition begins to fail. At everyday scales, space feels like a smooth background. You can point to a location. You can measure distance. You can always imagine something smaller in between. But physics does not promise that this picture holds forever. Quantum mechanics introduced a hard truth. There is a limit to how precisely certain things can be known at the same time. This is not due to bad instruments or lack of skill. It is a rule of the universe. The more precisely you try to locate something, the more uncertain its energy becomes. The more you focus on position, the more motion becomes unpredictable. Reality does not allow perfect clarity. At first, this uncertainty feels manageable. It affects particles, not space itself. But as you push closer and closer to smaller distances, uncertainty grows. energy rises. And energy does not remain neutral. Energy has gravity. This is where gravity enters the story in a way that most people never consider. Gravity is not just something that pulls objects together. It is the response of space itself to energy. Concentrate enough energy in one place, and space bends. Now imagine trying to measure an extremely tiny distance. To do so, you must focus an enormous amount of energy into an incredibly small region of space. But as you do that, gravity responds. Space curves inward, and before you can complete the measurement, the region collapses into a black hole. This is not science fiction. This is what our best theories predict when pushed to their limits. Trying to measure space too precisely causes space to destroy its own structure. At that point, the question changes completely. It is no longer what is smaller, it becomes, does smaller still exist? Because below a certain scale, space does not behave like space. Distance stops being a stable concept. The idea of here and there loses meaning. The universe does not provide coordinates anymore. This is where the Planck length appears, not as a particle, not as a building block, but as a boundary. The Planck length is the smallest meaningful distance that can exist. Below it, space cannot be divided in any sensible way. Physics does not reveal a deeper layer. It stops agreeing with itself. Quantum mechanics demands uncertainty. Gravity demands curvature. The speed of light demands limits. When all three are obeyed at once, space reaches a breaking point. The Planck length is that point. It is not important because it is small. It is important because it marks the edge of applicability of our concepts. Below this scale, words like distance, position, direction, and even time may no longer apply. This does not mean nothing exists below the Planck length. It means space itself may not exist in the way we understand it. Reality may not be smooth all the way down. It may have resolution, like an image that looks continuous until you zoom in far enough to see individual pixels. Not because the image is fake, but because it has a fundamental structure. At the Planck scale, space may fluctuate violently. Geometry may dissolve. Cause and effect may blur. The universe does not offer a deeper picture. It offers silence. This is deeply unsettling. We like to believe that reality always answers if we ask the right questions, that if we build better tools, the universe will reveal its secrets. The Planck length suggests otherwise. It suggests that some questions cannot be answered because they assume concepts that no longer exist. Below this scale, where may not be a valid question. Before and after may not be valid ideas. Distance may not be something the universe recognizes. The Planck length is not the smallest piece of reality. It is the smallest distance reality is willing to define. And once you reach that edge, you are not looking at something tiny. You are looking at the point where space itself stops making sense. At first glance, the Planck length sounds like just another measurement. Science is full of tiny numbers. Atoms are small. Atomic nuclei are smaller. Quarks are smaller still. So it feels natural to think the Planck length is simply the next step in that sequence, just another layer beneath everything else. But that way of thinking misses the point entirely. The Planck length is not small in the same way atoms are small. It is not a thing you can zoom in on. It is not a tiny object waiting to be discovered. It is a limit placed not on matter, but on meaning. To understand why, we need to separate two ideas that feel similar, but are not the same: smallness and definition. Atoms are small, but they are still defined. They have structure, they have position. They exist inside space. You can meaningfully say where an atom is, how far it is from something else, and how it moves through space. The Planck length is different. It is the point where space itself stops providing definition. Below this scale, the universe does not give you a way to talk about distance. Not because it is hiding something, but because distance is no longer a property that exists. This is why physicists do not treat the Planck length like the size of a particle. They treat it like a boundary, a line beyond which the language of space breaks down. To see why this boundary exists, we need to understand how measurement actually works at very small scales. In everyday life, measuring something feels simple. You look at it, you touch it, you place a ruler next to it. But at fundamental scales, measurement requires interaction. To measure position, you must bounce something off the object. Light is usually used because it is precise, but light has wavelength, and wavelength limits resolution. If you want to see something very small, you need light with a very short wavelength. Shorter wavelength means higher energy. There is no way around this. It is not a limitation of technology. It is a rule of nature. As you push toward smaller distances, the energy you must concentrate becomes enormous. At first, this energy just disturbs particles. That is the familiar quantum uncertainty. But if you keep going smaller, something new happens. Gravity enters the picture in a way that cannot be ignored. Energy is not just energy. Energy has weight. According to gravity, concentrating energy in one place curves space around it. The more energy you pack into a tiny region, the more space bends inward. Now, imagine trying to measure a distance smaller than the Planck length. To do that, you would need to focus so much energy into such a tiny region that space itself would collapse. The region you are trying to measure would form a microscopic black hole. This is not speculation. It follows directly from the rules we already trust. And this is the key point. Trying to measure space beyond the Planck length destroys the very space you are trying to measure. At that point, the question is no longer, what is there? It becomes, what does there even mean? This is why the Planck length is not just small, it is self-protecting. The universe prevents you from probing smaller distances not by hiding them, but by removing the concept of distance itself. Space refuses to be subdivided beyond a certain point. This tells us something profound about the nature of reality. Space may not be continuous. We are used to imagining space as a smooth fabric that can always be divided further. But the Planck length suggests that this smoothness may be an illusion that only exists at large scales. At very small scales, space may be grainy, fluctuating, or built from something deeper that does not resemble space at all. This does not mean space is made of tiny blocks like Lego pieces. That is too simple. But it does suggest that the idea of infinite smoothness breaks down. Below the Planck length, geometry itself may lose meaning. Directions may not exist. Distances may not exist. Even the idea of between may fail. This is why physicists do not talk about what exists below the Planck length in the same way they talk about atoms or particles. There is no experimental path that leads there. Any attempt collapses the framework needed to ask the question. The Planck length is not the bottom of a ladder. It is the edge of a map. Beyond that edge, the concepts we rely on no longer apply. Not because reality ends, but because our way of describing reality does. This is deeply uncomfortable because it challenges a core belief. The belief that reality must always be describable in familiar terms if we look hard enough. The Planck length tells us that this belief is wrong. Reality may be deeper than space itself. Space may be something that emerges rather than something fundamental. At large scales, it behaves smoothly. At small scales, it dissolves into something else entirely. The Planck length is where this transition happens. It marks the boundary between a universe we can describe and a universe that resists description. Not violently, quietly. And this raises a disturbing but fascinating question. If space stops making sense at this scale, what happens to time? Quantum mechanics is one of the most successful theories ever created. It explains atoms, particles, chemistry, electricity, light, and almost every modern technology we use. It has been tested again and again, and it works with astonishing precision. So when people hear that quantum mechanics breaks down at the Planck length, it sounds impossible. How can something that works so well suddenly stop working? The answer is not that quantum mechanics is wrong. The answer is that quantum mechanics was never designed to describe space itself. Quantum mechanics assumes space already exists. It assumes positions can be defined. It assumes time flows, even if unpredictably. It tells us how things behave inside space and time, not how space and time themselves behave at their deepest level. At large and medium scales, this assumption is safe. Even at atomic scales, space still behaves well enough for quantum rules to apply. Particles can be uncertain, but the stage they exist on remains stable. At the Planck scale, that stage collapses. The core idea of quantum mechanics is uncertainty. You cannot know everything at once. The more precisely you know position, the less precisely you know motion. This uncertainty is not a flaw. It is fundamental, but uncertainty has consequences. To localize something more precisely, you must inject more energy. That energy does not disappear. It becomes part of the system. It increases fluctuations. It shakes reality harder. At first, this just makes particles behave strangely. They blur. They spread out. They jump between probabilities. This is normal quantum behavior. But as you push closer to the Planck length, uncertainty explodes. Energy fluctuations become so extreme that space itself begins to fluctuate. Geometry is no longer stable. The idea of a fixed background disappears. Quantum mechanics assumes a calm stage. At the Planck scale, the stage is shaking violently. This is where quantum mechanics runs out of language. It cannot describe a situation where space itself is uncertain. At the Planck scale, space is no longer something particles move through. It becomes something that fluctuates, tears, reconnects, and dissolves. Directions may change, randomly. Distances may not persist from one moment to the next. Quantum mechanics has no way to handle this because it treats space as a given. Now, time enters the crisis. Quantum mechanics treats time differently from space. Space is uncertain. Time is a parameter. It flows. It orders events. It is assumed to exist in the background. But if space becomes unstable, time cannot remain untouched. At the Planck scale, time itself begins to lose meaning. To define time, you need change. To define change, you need a sequence of events. To define events, you need stable positions or states. But when space fluctuates violently, there are no stable states to compare. Time stops behaving like a smooth flow. Moments may not follow each other cleanly. Cause and effect may blur. The concept of before and after becomes difficult to define because the structure needed to support sequence is gone. This does not mean time reverses or disappears completely. It means time is no longer the familiar dimension we experience. It may exist in a fragmented or probabilistic way, just like particles do at smaller scales. Some physicists describe this as quantum foam, not because space literally looks like foam, but because it behaves chaotically. Tiny regions of space appear and disappear. Geometry fluctuates wildly. Distances flicker. time intervals lose consistency. This is not a metaphor for confusion. It is a description of instability. At the Planck scale, reality is not smooth enough to support classical ideas like location, duration, or trajectory. The universe becomes restless at its foundation. This is why quantum mechanics and gravity collide here. Quantum mechanics wants uncertainty. Gravity wants structure. Quantum mechanics allows energy to fluctuate wildly. Gravity responds to energy by bending space. At ordinary scales, these two coexist peacefully. At the Planck scale, they clash violently. The result is a breakdown of both frameworks. Quantum mechanics cannot describe space itself fluctuating. Gravity cannot remain classical when space loses structure. Both theories are correct. Both fail together. This tells us something extremely important. The Planck length is not just a small scale where physics gets difficult. It is the scale where our current idea of physics stops being applicable. The universe does not promise that reality will always fit inside our theories. It only promises consistency. At the Planck scale, consistency demands a new description entirely. This is why physicists talk about quantum gravity, not as a completed theory, but as a necessity, a framework where space and time themselves are quantum objects, not backgrounds. Until such a theory exists, the Planck length remains a boundary not of existence, but of understanding. Below it, space may not be smooth. Time may not flow. Events may not be ordered. The universe does not become smaller. It becomes stranger. And once time itself becomes unstable, a deeper question emerges. If time and space both lose meaning, what was the universe like at the very beginning? Gravity is usually the weakest force we talk about. It barely affects atoms. It does nothing noticeable to particles. In everyday physics, gravity feels slow, gentle, and predictable. That is why, for a long time, gravity was ignored when discussing very small scales. But this was a mistake. Gravity may be weak, but it has one unique property that changes everything at the Planck scale. Gravity does not care what something is made of. It only cares how much energy exists in one place. And at the smallest scales, energy becomes extreme. When we try to look deeper into reality, we are not simply observing. We are injecting energy. To measure smaller distances, we must use higher energy probes. There is no alternative. Precision costs energy. At first, gravity barely responds. At atomic scales, it is irrelevant. Even at nuclear scales, it remains silent. But as distances shrink further, energy density increases rapidly. The same amount of energy packed into a smaller space becomes more intense. Eventually, gravity can no longer be ignored. This is the turning point. At the Planck scale, the energy required to probe space becomes so concentrated that gravity dominates everything else. Space itself begins to bend violently in response to the energy used to observe it. This is deeply ironic. To understand space more clearly, we must look closer. To look closer, we must use more energy. That energy destroys the structure we are trying to study. Gravity turns curiosity into collapse. At these scales, gravity is no longer a gentle force acting between objects. It becomes the defining feature of reality. Space curves so sharply that it loses stability. Regions pinch, stretch, and fold unpredictably. And if energy concentration goes even slightly beyond this point, something dramatic happens. A black hole forms. Not a massive cosmic black hole, but a microscopic one. A tiny region where space collapses inward so completely that no information can escape. The act of observation creates an event horizon. This is not science fiction. It is what happens when you force quantum uncertainty and gravity to coexist at extreme scales. The universe responds by hiding information behind horizons. It does not allow infinite precision. This tells us something crucial. The Planck length is not arbitrary. It is enforced by gravity itself. Below this scale, space cannot remain open. Any attempt to define a smaller distance causes gravitational collapse. The universe closes the door not by refusing to answer, but by removing the question. This is why physicists say the Planck length is the smallest meaningful distance, not because nothing exists below it, but because gravity prevents space from being defined there. Gravity does not merely distort space, it decides when space stops existing as space. This also reveals something profound about gravity's true nature. Gravity is not just a force that acts within space. It is the rule that shapes space itself. At large scales, this shaping is gentle. Planets orbit stars, stars orbit galaxies. Space curves smoothly. But at the Planck scale, gravity becomes violent. Curvature explodes. Geometry breaks. There is no stable background left. This is where Einstein's theory of gravity reaches its limit. General relativity describes gravity as smooth curvature of spacetime. It works perfectly for planets, stars, and galaxies. But it assumes spacetime itself is continuous and well-defined. At the Planck scale, that assumption fails. Curvature becomes infinite. Equations stop behaving. The theory predicts its own breakdown. This is not a flaw. It is a warning. Einstein's theory is telling us it is being used outside its domain. Quantum mechanics, meanwhile, allows violent fluctuations. Gravity responds by destroying structure. Neither theory is wrong. They are simply incompatible at this scale. This is why the Planck length is where gravity becomes unavoidable. At smaller scales, gravity is irrelevant. At this scale, it dominates everything. Space stops being a calm stage. It becomes a battlefield. This also explains why the early universe is so mysterious. At the very beginning, everything was compressed into an unimaginably small region. Energy densities were extreme. Gravity ruled completely. Space and time did not behave the way they do now. The Planck scale is not just about smallness. It is about dominance. Below this scale, gravity no longer allows space to exist quietly. It asserts control. It reshapes, collapses, and erases structure. This tells us something unsettling but important. Space is not fundamental in the way we imagine. It is conditional. It exists only when gravity allows it to exist smoothly. At the Planck scale, that permission is withdrawn. And once gravity dominates completely, another realization becomes unavoidable. If gravity destroys space at this scale, how can quantum mechanics and gravity ever work together? For more than a century, physics has relied on two towering pillars to explain reality. One governs the very small, the other governs the very large. Quantum mechanics explains particles, atoms, and forces with incredible accuracy. General relativity explains gravity, space, and time with equal precision. Each theory works beautifully in its own domain. Each has been tested repeatedly. Each has transformed our understanding of the universe. And yet, at the Planck length, they fail together. This failure is not subtle. The equations do not merely become difficult. They contradict each other. They demand opposite things from reality. When forced to operate at the same scale, they cannot agree on what space and time even are. This is the deepest crisis in modern physics. Quantum mechanics is built on uncertainty. It allows energy to fluctuate, positions to blur, and outcomes to exist as probabilities. Nothing is fixed until it is measured. Reality at small scales is restless, jittery, and unpredictable. General relativity, in contrast, is built on smoothness. It describes space and time as a continuous fabric that bends gently in response to mass and energy. It assumes geometry is well defined. It assumes space-time exists as a stable structure. At everyday scales, these assumptions do not conflict. At atomic scales, gravity is too weak to matter. At cosmic scales, quantum effects average out and disappear. The universe allows both theories to coexist peacefully, but the Planck scale forces them into direct contact. At this scale, quantum mechanics demands violent fluctuations of energy. Energy appears and disappears unpredictably. Fields jitter. Uncertainty dominates. But gravity responds to energy, no matter how it appears. Even quantum energy curves space. This creates a contradiction. Quantum mechanics says energy can fluctuate wildly. Gravity says space must respond to that energy. The result is chaos. Space itself begins to fluctuate. Geometry loses stability. Distances cannot be defined consistently. Time cannot flow smoothly. The assumptions required by both theories collapse. Quantum mechanics assumes space exists. Gravity defines space. When space itself becomes uncertain, neither theory can function. This is why physicists say the Planck length is where physics breaks. Not because nature breaks, but because our descriptions do. The universe does not stop behaving. Our frameworks stop applying. This breakdown is honest. It tells us that both theories are incomplete. Not wrong, but limited. Each captures a deep truth about reality, but neither is fundamental enough to describe the foundation itself. The Planck length is the scale where those foundations are exposed. Below this scale, there is no smooth space-time for gravity to curve. There are no fixed positions for quantum particles to occupy. The language of where and when loses coherence. This is deeply uncomfortable because physics has always progressed by going deeper. Every time we thought we reached the bottom, we found another layer. The Planck length is the first time the universe refuses to reveal one. Instead of showing a deeper structure, it shows contradiction. This suggests that space and time themselves are not fundamental. They may emerge from something deeper, something that does not resemble geometry at all. Space and time could be approximations that work only at large scales, just like solidity is an approximation that breaks down at atomic scales. At the Planck scale, we are not missing pieces of space. We are missing a deeper concept entirely. This is why physicists search for a theory of quantum gravity. Not to unify equations for elegance, but because reality demands it. Without such a theory, the Planck scale remains a blind spot. Quantum gravity would not just describe particles moving in space. It would explain how space itself comes into existence, how geometry emerges, how time begins to flow, how causality survives. Until then, the Planck length remains a warning sign, a sign that we have reached the edge of our map, a sign that our deepest ideas are approximations, a sign that reality is not obligated to fit human intuition. This collision of theories is not failure, it is progress. It tells us exactly where our understanding ends. And once we accept that space and time may not be fundamental, a radical question emerges. If space is not smooth, could it be built from something discrete? When people first hear about the Planck length, a natural idea appears in the mind. If there is a smallest possible distance, then maybe space is made of tiny pieces, like pixels on a screen, like grains of sand, like building blocks stacked together to form reality. This idea is tempting. It feels familiar. We are used to thinking that things are made of parts. Matter is made of atoms. Atoms are made of particles. So why not space? But the truth is more subtle and more unsettling. The Planck length does not mean space is made of little cubes or dots. It does not mean you could, in principle, zoom in and see a grid. That kind of picture is too simple. Space at the Planck scale does not behave like a Lego structure. What the Planck length tells us is not that space has pieces, but that space has resolution. Resolution is different from structure. A digital image has resolution. Below a certain scale, detail disappears. Not because nothing exists, but because the system no longer defines smaller distinctions. You can zoom in, but you don't get more information. You only get blur. The Planck length may represent something similar for reality itself. At large scales, space looks smooth. Distances make sense. Directions exist. Geometry works. But as you zoom in, space does not reveal finer detail forever. It reaches a point where the idea of closer stops adding information. Below that scale, space does not become grainy. It becomes undefined. This is an important distinction. If space were simply made of pieces, physics could still describe those pieces. We could count them, label them, measure how they connect. But the Planck length suggests something more radical. It suggests that the concept of distance itself stops applying. This means space may not be a thing at all. It may be a relationship. At large scales, those relationships behave smoothly enough that we call them space. At small scales, the relationships become unstable, fluctuating, and unrecognizable. Geometry dissolves. What remains is not space in the usual sense. This is why physicists struggle to talk about inside the Planck length. The language itself assumes geometry. It assumes separation. It assumes direction. Those assumptions may simply not exist at that scale. Some theories attempt to describe space as built from discrete elements, not points, but connections. Networks, loops, interactions. In these ideas, space emerges from how fundamental entities relate to each other, not from where they are located. Location becomes secondary. Relation becomes primary. This is a profound shift. Instead of asking where something is, we ask how it connects. At large scales, those connections form something that looks like smooth space. At small scales, the connections become sparse, tangled, or unstable. Space stops looking like a fabric and starts behaving like a process. This also explains why smooth space may be an illusion. When you look at a calm ocean from far away, it looks flat and continuous. But up close, it is chaotic. Waves rise and fall. Motion dominates. The smoothness only exists when you average over large distances and long times. Space may be similar. At human scales, it looks calm. At atomic scales, it still behaves well enough. But at the Planck scale, the averaging fails. The chaos becomes visible. The smooth picture collapses. This does not mean reality is broken. It means our approximation has reached its limit. The Planck length is where space stops being a background and starts being an outcome. It is no longer something things exist inside. It is something that emerges from deeper rules. This also explains why trying to divide space further does not work. You are not cutting a thing into smaller pieces. You are asking a question the universe does not define. Below the Planck length, the universe does not answer with smaller distances. It answers with noise, fluctuation, indeterminacy. Geometry loses meaning. This is why the Planck length is not a smallest unit in the way atoms are units. It is not a brick. It is a boundary between meaningful and meaningless questions. Space exists only where geometry is stable. Below that scale, geometry dissolves. And if space dissolves, something else must take its place. That brings us to time. If space is not fundamental, then time may not be either. We are used to thinking of time as something that always flows. Seconds follow seconds. Moments stack neatly into the past. No matter how strange reality becomes, time feels like the one thing that never breaks. But the Planck length challenges that belief. Time is deeply connected to space. We often separate them in daily life, but physics does not. Space and time are woven together into a single structure. When space becomes unstable, time cannot remain untouched. At ordinary scales, time feels smooth. Clocks tick steadily. Cause follows effect. The universe appears ordered. Even in quantum mechanics, where uncertainty dominates, time is treated as a stable background. Particles behave unpredictably, but time itself still flows. At the Planck scale, that assumption collapses. To define time, you need change. To define change, you need events. To define events, you need stable positions or states that can be compared. But at the Planck scale, space no longer provides stable positions. Geometry fluctuates violently. Locations do not persist. Without stable space, time loses its anchor. The idea of before and after depends on having something that remains long enough to mark a sequence. At the Planck scale, nothing remains fixed. Space flickers, energy surges, geometry dissolves and reforms unpredictably. Time stops behaving like a smooth line. It may break into fragments, it may fluctuate, it may lose direction altogether. This does not mean time disappears in a dramatic way. It means the universe no longer offers a consistent definition of duration. Asking how long something lasts may not make sense if the structure needed to define long does not exist. Physicists refer to a related idea called Planck time. This is not the smallest tick of a cosmic clock. It is the shortest meaningful interval of time that can be defined using our current understanding of physics. Below this interval, time loses clarity. Just as distance becomes undefined below the Planck length, duration becomes undefined below the Planck time. The universe does not provide a finer resolution. This suggests something deeply unsettling. Time may not be fundamental. It may emerge only when space is stable enough to support sequences. At large scales, this stability exists. At small scales, it fails. This means the flow of time we experience may be an illusion created by averaging over enormous numbers of tiny, unstable events. Just as a smooth surface hides microscopic roughness, smooth time may hide violent fluctuations underneath. At the Planck scale, the universe may not evolve smoothly. It may jump, flicker, reconfigure itself in ways that do not resemble motion or flow at all. Cause and effect become difficult to define here. If time is unstable, then the order of events cannot always be trusted. The universe may not have a clear notion of what happened first. This is why classical causality depends on scale. At large scales, causality is safe. Signals take time. Effects follow causes. The speed of light protects order. But at the Planck scale, where time itself fluctuates, even that protection may weaken. This does not mean paradoxes explode everywhere. It means the language of causality may no longer apply in the way we expect. The universe may still be consistent, but consistency may not look like sequence. This also changes how we think about beginnings. If time breaks down at the Planck scale, then asking what happened before the beginning of the universe may be meaningless. There may not have been a before at all. The universe may not have emerged from an earlier moment. Time itself may have emerged with space. The Planck scale may represent not just the limit of smallness, but the limit of history. Beyond it, there may be no timeline to extend backward. This idea is uncomfortable because we rely on time to understand everything. We explain causes, we trace origins, we build stories. If time itself dissolves, those tools fail. But the universe does not owe us stories, it only owes consistency. The Planck length and Planck time suggest that time and space are not the stage on which reality plays out. They may be products of deeper processes. When those processes dominate, the stage disappears. At large scales, we see the result: smooth space, flowing time, stable causality. At the Planck scale, we see the raw mechanism underneath. And it does not look like space or time at all. This realization forces us to confront a final mystery. If space and time both emerge from something deeper, what was the universe like at the very beginning? When we talk about the beginning of the universe, we usually imagine an explosion, a bright flash, matter rushing outward into empty space, time starting to tick from a first moment. This picture feels intuitive because it matches how explosions work in everyday life. But the Planck scale tells us that this picture is wrong. At the very beginning of the universe, space and time did not behave like space and time. They may not have existed at all in any meaningful sense. The familiar stage on which reality now unfolds was not present yet. This earliest phase is often called the Planck era. It is not a place. It is not a moment in time. It is a boundary where our ideas stop working. To understand why, we need to let go of one deeply ingrained assumption: that the universe began in space and in time. The Planck scale suggests something more radical. Space and time themselves may have emerged from the same process that created the universe. At the very beginning, energy densities were extreme. Everything that now exists was compressed into an unimaginably small state. Gravity dominated completely. Quantum fluctuations were violent. Geometry could not settle into a stable form. There was no smooth space to expand into. There was no steady time to flow forward. The universe was not somewhere. It was not happening when. Those words assume structures that did not yet exist. This is why asking what happened before the Big Bang may be meaningless. The question assumes time existed before the universe. But if time itself emerged from the Big Bang, then there was no before to speak of. The Planck era is where this transition happened. As the universe expanded and cooled, energy densities dropped. Gravity loosened its grip. Quantum fluctuations became less violent. Slowly, space stabilized. Geometry emerged. Distances became definable. Time began to flow in a consistent direction. This was not a sudden switch. It was a transition. Below the Planck scale, reality was too unstable to support space and time. Above it, space and time could emerge as approximate concepts. The smooth universe we experience today is the result of that stabilization. This means something profound. Space and time are not the foundation of reality. They are outcomes. They emerge only when conditions allow them to exist. Core, extreme energies, those conditions fail. Reality exists in a different form entirely. We do not yet know what that form is. Our theories can describe the universe once space and time exist. They fail precisely where space and time are born. This is not a weakness of science. It is a boundary of applicability. The Planck era marks that boundary. During this era, the universe may not have had dimensions in the way we understand them. Directions may not have existed. The concept of expansion itself may not apply. There was no geometry to expand. Instead, reality may have been governed by relationships, interactions, or rules that do not resemble space-time at all. Space and time may be emergent properties, much like temperature emerges from the motion of particles, but doesn't exist at the level of individual atoms. This analogy matters. Temperature feels fundamental in daily life. Hot and cold feel real. But at the deepest level, temperature is not a thing. It is a collective effect. Below a certain scale, the concept stops making sense. Space and time may be similar. At large scales, they feel absolute. At the Planck scale, they may dissolve into something deeper that cannot be described with geometry. This also explains why the early universe feels so mysterious. We can describe it fractions of a second after the beginning, when space and time are already stable enough to behave predictably. But the very first moments remain unreachable. Not because we lack imagination, but because our concepts rely on space and time. The Planck scale tells us that reality does not guarantee those concepts forever. This challenges how we think about origins. The universe may not have begun as an event in time. It may have begun as the emergence of time itself. There may be no answer to what came before, because before may not exist. This is not ignorance. It is consistency. The universe is not required to fit inside human language. It only needs to follow its own rules. At the Planck scale, those rules may be so different that our usual questions fail. The Planck era is not hidden. It is inaccessible by definition. It marks the moment where the universe transitions from something unrecognizable into something we can describe, from raw reality into space-time. And this brings us to a crucial realization. If space and time are emergent, then our current theories may only describe the surface of reality. Something deeper must exist underneath. Once physicists accepted that space and time may not be fundamental, a difficult question appeared. If space-time is not the foundation of reality, then what is? This question has no easy answer. Every theory we have ever built assumes space and time exist. Equations describe how things move through space, how they change over time, and how forces act across distance. When those concepts dissolve, our usual tools stop working. Still, scientists have tried, not because they expect quick success, but because the Planck scale demands a deeper explanation. The breakdown of physics is not a mystery to ignore. It is a sign pointing toward something more fundamental. One of the first realizations was that whatever exists beneath space and time cannot look like space and time. It cannot have positions, distances, or durations in the usual sense. Those ideas only emerge later, when reality becomes calm enough. So physicists began searching for descriptions that do not start with geometry. Some approaches imagine reality as made of relationships rather than locations. Instead of asking where something is, they ask how it connects to other things. Space then emerges as a large-scale pattern of these connections, much like a network appears from individual links. In this view, space is not a container. It is a consequence. Another approach imagines that geometry itself is quantized, not space made of blocks, but space built from discrete units of area and volume. These units do not exist in space. They generate space when combined. Smooth geometry emerges only when many of them act together. At very small scales, geometry is not smooth. It is fragmented. Time in these ideas is even stranger. It may not flow at all at the deepest level. Instead, change may be fundamental, and time may be an ordering we impose afterward when patterns stabilize. This challenges intuition deeply. We are used to thinking that time causes change. These ideas suggest change causes time. There are also theories that suggest reality is fundamentally informational, that the universe is built from interactions, correlations, and limits on information rather than objects moving through space. In this picture, space and time are bookkeeping tools that summarize deeper processes. These ideas are not science fiction. They are serious attempts to answer a serious problem. But none of them are proven. None have experimental confirmation. They exist because the Planck scale demands something beyond our current frameworks. And this is where humility enters physics. We often imagine science as a steady march toward truth, uncovering deeper layers one by one. The Planck length disrupts that narrative. It tells us that deeper layers may not resemble the ones above them at all. Just as atoms do not resemble stones, and quarks do not resemble atoms, the foundation of reality may not resemble space and time in any recognizable way. This makes discovery difficult. Experiments cannot probe below the Planck scale without collapsing the conditions needed to measure anything. Observations are blocked not by technology, but by gravity and uncertainty. The universe itself prevents direct access. This does not mean the theories are wrong. It means they are untestable for now, and that is an uncomfortable position for science to be in. Science relies on evidence. At the Planck scale, evidence may be fundamentally unreachable. We are forced to reason indirectly, using consistency, logic, and hints from cosmology. This is why modern theories remain speculative. They are constrained by mathematics and coherence, not by direct observation. Some may be closer to the truth. Some may be wrong entirely. But all of them share one insight. Space and time are not fundamental. They are emergent. They appear only when reality settles into patterns large enough and calm enough to support geometry. At the Planck scale, those patterns do not exist. Reality is raw, unstable, and unrecognizable. This realization changes how we think about knowledge itself. There may be limits not just to what we can measure, but to what can be meaningfully described. The universe may contain aspects that resist translation into human language, mathematics, or intuition. The Planck length is the first place where this resistance becomes absolute. It tells us that reality is not obligated to reveal everything. And this brings us to the final understanding. The Planck length is not a problem to be solved. It is a message to be interpreted. After everything we have explored, one truth becomes unavoidable. The Planck length is not about smallness. It is about limits. Not limits of technology, not limits of intelligence, but limits built directly into reality itself. For centuries, humans believed that the universe could always be understood by going deeper. Smaller pieces, finer detail, more precision. Every time we improved our tools, reality rewarded us with another layer. Cells beneath tissue, atoms beneath molecules, particles beneath atoms. This created a quiet assumption that reality is infinitely divisible, that it always answers when questioned deeply enough. The Planck length breaks that assumption. It tells us that the universe does not promise infinite resolution. It does not guarantee that space can always be divided further. It does not ensure that every question we ask has meaning at every scale. Below the Planck length, reality does not reveal a deeper picture. It withdraws the language needed to describe one. This is a profound shift. We are used to thinking of limits as barriers to overcome. Faster engines, better microscopes, more powerful computers. The Planck length is not a barrier waiting to be crossed. It is a boundary that defines what can be asked. It is where how small stops being a valid question. This does not mean nothing exists beyond it. It means beyond may not exist as a concept. Space itself may not be fundamental. Time itself may not be fundamental. They may be approximations that work only when reality is calm, averaged, and stable. At the deepest level, reality may be built from something that does not resemble geometry at all. The Planck length is where those approximations fail. This forces us to rethink what it means to understand the universe. Understanding may not mean reducing everything to smaller parts. It may mean recognizing where reduction stops being meaningful. The universe is not incomplete because it has limits. It is coherent because it has them. Without limits, there would be no order. Without order, no causality. Without causality, no history. Without history, no structure. The Planck length is part of the same framework that preserves consistency, just like the speed of light preserves causality. Both are not obstacles. They are safeguards. The speed of light prevents events from collapsing into instant chaos. The Planck length prevents space from dissolving into infinite detail. Together, they shape a universe that can exist without contradiction. This also changes how we view human knowledge. There may be aspects of reality that cannot be translated into measurements, equations, or visual models. Not because we are limited, but because reality itself does not define those aspects in measurable terms. The Planck length is the first place where the universe says, "This question does not apply." That is not failure. That is honesty. It tells us that reality is not obligated to align with human intuition. It existed long before we observed it, and it will continue long after. Our theories are maps, not territory. The Planck length marks the edge of the map, not the end of the land. Beyond it, something exists. But it may not be space. It may not be time. It may not be describable. And that is not frightening. It is humbling. The Planck length reminds us that the universe is deeper than our categories. That understanding is not the same as control. That mystery is not ignorance, but structure beyond language. In the end, the Planck length does not tell us how small reality gets. It tells us how carefully reality is built. Reality does not end at the Planck length. Our familiar ideas do. And beyond that edge, the universe remains consistent, even when we cannot describe it.